Okay. Let's get started, everyone. So today we will continue our discussion of test time scaling, which we started in the last class by discussing the GRPO algorithm and also this concept of verifiable rewards. And towards the end of last class, we looked a little bit at some results from the DeepSeek R1 paper in which they show that first of all, their reward goes up over time. Secondly, the length of the reasoning, the thinking tokens that they produce also goes up over time. So we'll look at some other results today that kind of back up this hypothesis that as you allow a model to produce more and more reasoning tokens, which are, again, tokens that are between those special think and end think boundaries that we discussed in the last class, as we increase the thinking budget, the model's performance seems to go up on various reasoning-oriented tasks, so math problem solving, coding, and things like that. So this behavior is really the thing that's powering any modern coding agent. If you're using Copilot or Cursor, you'll note that every time you tell it to do something, it first comes up with a plan, depending on what models you're using. And it takes some time before it does that, right? And actually produces tokens of code. Okay, so yeah, and then I also wanted to go into a little bit of detail on what the learned thinking tokens actually contain, like what kinds of behaviors they exhibit. We'll also talk about a simplified version of getting pre-trained models to perform thinking without actually doing any RL. And we can talk about kind of the pros and cons of these approaches. Okay, but before we get into all of that, I just wanted to, at a high level, summarize all of the different RL algorithms and types of rewards that we've covered in the last 3 classes, just as an overview to make sure that you have everything straight when it comes to the different algorithms that we've discussed. Okay, so several different RL algorithms and reward models. So when we were considering the reinforcement learning algorithms, right, we started with reinforce, the simplest one, the one which we actually derived the gradient by using the log trick that we mentioned. And here, the loss for a single prompt and a single rollout y is this the advantage, which you could incorporate that KL term into it too. Here we didn't talk about a specific baseline that was used, so this could be anything like mean batch statistics or using some sort of trained value function. And we compute the log p x y. So this is what we were doing for the reinforce, and all of the other algorithms that we discussed are just variants of this that have clipping behavior or multiple updates per batch and things like that. So we talked about AKL incorporating, is the reward minus the KL divergence of p theta between p theta and PSFT. And the idea here was that the KL divergence is going to penalize the model from deviating too much away from the base instruction tune model. That said, in this algorithm, we only do one step per batch, and we don't have any clipping, so we don't do anything else to make the algorithm more stable. So then we talked about PPO, in which the loss looks very similar, except we have this additional, we're taking the minimum of this clipped and unclipped term, right? Where the thing that we're clipping is this policy ratio, this rho, and we multiply that by our advantage. And similarly, we compute the unclipped version of this and multiply it by our advantage and take the minimum. So here, this rho, again, is the policy ratio between p theta, which is our current model, and p theta old, which is initialized to be p theta for a given batch, but then we actually perform multiple updates on this batch where the p theta deviates away from p theta old, and so then you start getting into some tokens may be in the outside of the clipped range, and so we won't be updating those, right? So one key difference here is that we do multiple updates per batch, not just one. Another thing that we talked about with PPO is that our baseline is from a trained value function. And so this value function, again, is being trained to predict the reward from some intermediate generation. So given the prompt and part of what the model has produced, it's trying to predict what the reward will be at the end of this generation. And so this value function is trained at the same time as the policy model. So when you're training the policy model, you keep the value function frozen, and when you're training the value function, you keep the policy model frozen. Yeah.
Could you? I'm still confused on what exactly the loss for there represents. Like, is it that's like based off of the reward, right? Like,
yeah. So remember that this advantage here is a function of the reward minus the baseline and minus the KL penalty. Yeah. So the reward is always included in this.
And what are we doing with that then? Again, like we're taking the gradient of that, right?
So when we take the gradient of this J here, we are keeping our advantage, like we're not going to backprop into the advantage. So what we are backpropping into is this policy ratio. So if you think about the policy ratio, it's saying how much more likely is this token under my current policy than the old policy. So if we increase that ratio, right, if it's above 1, that means that the token is more likely under the new policy. So intuitively, if our advantage is above 0, that means it's positive. That means this particular token is better than usual. So we want to increase its probability. We can do that by increasing the policy ratio. So we are backpropping through the policy ratio, specifically the numerator of the policy ratio, which is the probability of that.
So what does the J function represent then?
So the J here is the reward that you're trying to maximize, right? Yeah, but we've not actually, so when you're looking at the implementations of these things, generally people will just put a negative sign in front of this and treat it as like you're trying to minimize
Yeah.
this term. But, you know, that's just a decision so that we can use our favorite optimizers. Okay, other questions? Okay. So here I'm not going to talk about the different types of rewards just yet. I will first just go over GRPO at this high level, and then we will start talking about different rewards. Because there is, you know, when the DeepSeek paper came out, they introduced this algorithm, GRPO. They also introduced, at least for the first time publicly, this idea of training with verifiable rewards. And so both of those are independent and important contributions that they combine, but they don't necessarily have to be combined. So you can use GRPO with a normal reward model. You can use PPO with verifiable rewards. So I just want to make that clear as well. So let us continue with GRPO. So this is the group relative policy optimization. And it takes a lot of the same elements from PPO, right? It's still using this clipping where based on the policy ratio. So it's very similar to PPO, but here there's no value function. So that is a key difference. No value function. And so actually the baseline here is computed using the statistics from a group. So that's the other like conceptual difference, is that this algorithm requires performing G rollouts per prompt X, not one like in PPO or reinforce. So in PPO or reinforce, you could certainly do multiple rollouts for a given prompt, but your advantages are not functions of the other responses, the other rollouts for the same prompt. So GRPO explicitly connects all of the rollouts for a single prompt together using this normalization for the mean centering and z-scoring with the standard deviation. So we have no value function. Instead, we have a advantage which is normalized by the group statistics. So specifically, we had this, the advantage here for any given yi, maybe I should write that, is the reward minus the mean of the group rewards divided by the standard deviation. One small implementation note is usually you divide by the standard deviation plus some tiny epsilon term just to avoid any numerical stability issues, but that is kind of irrelevant conceptually. Okay, so one thing to emphasize here is that GRPO is less computationally expensive than PPO due to the fact that we do not need to keep the value function in our GPU memory. So instead of this trained value function, which is generally the same size as the policy model, here we've dropped all of that, but we've exchanged that for some added decoding complexity because now we need to generate multiple different rollouts for a single prompt. So that's kind of a trade-off. Generally, it's preferred because you can free up that GPU memory for larger batches, bigger group size, things like that. So one thing I want to make clear at this point is that you can use reinforce PPO and GRPO with any kind of reward. So GRPO is not specific to verifiable rewards. PPO is not specific to learned reward models. That said, there is the trend to nowadays use GRPO whenever you have tasks that have verifiable rewards, so you can further limit the computational expense. But lately we're seeing different kinds of implementations. So for example, if you end up using Tinker in your projects with reinforcement learning, their reinforcement learning code is kind of a weird hybrid of GRPO and reinforce. So they do some sort of group centering. I'm not really sure if they're doing the policy ratio thing as in PPO, but regardless, there's now like hundreds of different variants of these algorithms. But the key kind of ideas are group normalization. So that has been a very significant impact since it was released. And also this idea of clipping and making very stable updates to prevent degeneration. Yeah.
In the GRPO, basically we have a baseline per prompt.
Yes. To that point, we will go a little later into some specific examples of what does this advantage look like with different rewards, just so we fully understand the motivation behind normalizing based on the group stats and what that actually does to the updates. So I'll do that in a second. But the next thing I wanted to do is discuss these reward models here. So the very first thing we talked about when we discussed reward models, this was before we talked about any sort of RL algorithm, was the Bradley-Terry preference model. Preference. And note that this use of model is not the same as like some neural network model, right? The Bradley-Terry preference model is a statistical model of how you should handle preference judgments. And so we are going to use this to train a neural network reward model. So I'm not going to go over the kind of exact math again, but just going to go over the intuition again of this and how this differs from what we've seen more recently with DeepSeek. So here, we're going to train our reward model, which we can just say is this R function, on a big data set of human preference judgments. Now, one question is, where do we get the responses that these human preference judgments are then obtained upon? So ideally, the humans rate wise, so responses generated from the SFT'd model that we're training. In practice, however, it's very common for both open data sets and what goes on in industry labs to just gather as many preference judgments as they can from many different models and model families and tasks and train one big reward model on those, which can then be used to during like reinforce or PPO to do the alignment of multiple different models. But in the optimal case, all your judgments will be on responses that were generated by your SFT model. Then, just at a high level to explain what these judgments even look like, for a human, we give them prompt X and 2 or more responses yi. The human will produce a ranking, and we denoted this by, the response that's a winner, y sub w. Human might rank higher than the losing response, y sub l. Note that these are relative rankings, right? So y sub w and y sub l could both be bad, but one just might be a little better than the other. Or they could both be good. You don't know because there's no absolute scores assigned by the human to these responses. They're just saying, I like this one more than this one. Now, given these, we're going to train our reward model to make the reward, so let me just say reward model, to make Rx YW greater than Rx YL. And we discussed the Bradley-Terry, the loss that comes from that as the way that we actually train this reward model. So a reward model will give you a single number for any prompt and response pair. And it's trained to make the score for winning outputs higher than losing ones. So that's the idea. And if you gather enough of these judgments on as many different tasks as possible, you would hope that your reward model can generalize to a huge range of tasks. So it's able to produce like reasonable scores of many different tasks, and we can use it to do like general purpose improvement of our model. However, we also talked about how reward models are very prone to artifacts, and those kinds of artifacts can be kind of gamed by our policy model. So it might find ways to improve the reward that do not correspond to actually improving what a human would think is a better response. And so that's like one of the key challenges with this whole thing, and something also that you will see in your homework, which I'm almost done with. Okay, so this was the reward model, and it's kind of set in contrast, now that we've talked about it, to verifiable rewards. And so here, I want to make this distinction between RLHF, which is reinforcement learning from human feedback. This is generally associated with reward models that have been trained on human preference judgments, and then we use those to optimize the model. Meanwhile, with verifiable rewards, we have a new paradigm called RLVR, which is reinforcement learning with verifiable rewards. So here, there are no human preference judgments that we need to acquire in order to improve our model. However, we are limited in the kinds of tasks that we can actually perform this strategy on. So one of the ideas here is that these are ideally cheap and quick to obtain. When we talked, for instance, with math problems, right? It's very cheap to say, is the answer 7 or not? It's slightly, well, not slightly, but definitely more involved to say, okay, you generated this code, execute the code and see if there are any compiling errors, or execute the code and see if it passes these unit tests that I've written. Like those could be more expensive to obtain, just because it takes a while to run the program, but still it's pretty cheap to write a function that gives you like a 1 if it passed all those tests and 0 if it didn't. So here we have no learned reward model. The rewards generally come from the external environment in the case of code, or some sort of simple script that you've written to check for correctness. So common things that you can write rewards of, or like create rewards for, are correctness, like in the case of math problems, formatting. So in the end of the last class, we talked about how nowadays models perform some thinking within these special think tokens, and then also they produce their final answer within separate special token tags. And so one type of reward you might want to use here is to give the response a 1 if it followed the format that you intended it to, and a 0 otherwise. So this is completely separate of correctness, but also important if you want the model to follow a particular format. And then the last thing that I will highlight here are execution-based rewards, often for coding. So again, like if you run this, does it have errors? Does it pass unit tests? This is kind of interaction with the environment. And you can go a lot further with this kind of paradigm, especially when we start talking about agents, right? You can have a system that interacts with other websites and APIs, like for example, book a flight from DC to Boston, right? And so if your agent successfully completes that, you could verify it by like, did you get some email confirming this or not? You can imagine training that kind of system is a lot harder because it has to actually execute actions before it gets that reward. But still, people are looking into things like this now. Like multi-step, very complex actions in the real world. And you can use, again, verifiable rewards for several of these kinds of tasks. Okay, any questions about this? All right, so at this point, we have these different RL algorithms, and we have these two high-level categories of rewards, and we can mix and match any of them. That said, GRPO was proposed with the idea of using it with verifiable rewards. So the next thing I want to do is examine the advantage computation of GRPO, just to make it clear exactly what it does in different common settings of the reward distribution across a group to motivate the whole approach of generating a bunch of rollouts. All right, so and in all of these cases, we'll assume a group size of 8. So for a given prompt, we will generate 8 rollouts. We will score all of those with our whatever verifiable reward. Let's just say it's like a math problem. We generate 8 answers from the language model. We score each of them for correctness with a simple binary reward, where it's 1 if it's correct or 0 otherwise. But later on, we'll also look at what happens if we use more complex rewards and why the GRPO formulation is good. Okay, so first, I want to just introduce a couple of different quantities that we can track. So obviously we have our reward, which is this. And then we can create a raw advantage, which is has no baseline. So this is generally bad, and we'll see why in this example. We'll also consider a mean-centered advantage, right? So where this mean is computed over all the rewards in the group. And here we don't have any normalization by the standard deviation. So we have just mean-centered this. We haven't done anything else. And finally, we have our GRPO advantage, which is divided by the standard deviation here. So let's take a look at some specific cases that we might encounter when doing our rollouts. So the first is a case of rare success. And this is often like the most important one. Generally, you're trying to make your model, like if it has a very low success rate, you want to increase the success rate on whatever kind of math problem you're looking at. None of these methods will work if the model is completely unable to get the correct response in any rollout. So the rare success cases are the ones that we want to kind of focus on. So here, in our case where we have 8 rollouts, we might have only the very first rollout, 7, associated with a positive reward, a correct answer, and all the other ones have no reward at all. So now we can make a simple chart to kind of track all of these different quantities and have a better understanding of what is going on. So actually, I can just do the advantage, raw advantage, the mean-centered advantage, and the GRPO advantage. And here we can track the winners, what they receive, and the losers, what did they receive. So here, we only have one winning rollout, which is the very first one. All the other ones were incorrect. So our raw advantage here is +1 and 0 for all of the losers. So this means that we don't actually do any update for any of these losing samples, right? So their advantage is 0. We do not adjust their probabilities down as a result. This is obviously undesirable, right? All 7 of these losing rollouts were incorrect, and we want to lower their probabilities for the next time around. So if we do mean centering, here the mean of this group is 1/8, so 0.125. And the standard deviation is 0.33. Let me just move this table down. Okay. So when we subtract away the mean, doing our mean centering, now we actually have a negative advantage for these losing samples, right? So now the losing samples, we will decrease their probability when we compute the GRPO loss and the gradient, but it's not like a very large decrease in their probability. So finally, when we do the z-score normalization, so dividing this by the standard deviation, we see that the advantage for the single winner here increases a lot. So it becomes 2.647. And the advantage of the losers also gets more negative. So here we are basically putting more emphasis on the rare success. So every time we observe a group like this one, we are giving a strong positive boost to the probability of this rare success. Now, you might think, well, look, we talked about the whole policy ratio and the clipping, and so if we give this sample, this rollout a very strong positive boost, won't it probably run into the clipping and get outside of that region? That is possible, and it could certainly happen. It's not necessarily a bad thing, right? We just want to take kind of the max possible update we can when we get a batch like this, where we have actually one success and all of the other ones are failures. Like, it makes sense that we would want to increase the probability of the success as much as we can. Now, if none of the examples in the batch were successful, so all of them were zeros, we have no update for this batch, right? We just didn't have any positive examples. The numerator in the advantage will be 0, and we don't do any update. Similarly, if all of the samples in the batch are correct, we also have no update, right? Because when we do the mean centering, here the numerator will still be 0, and we will similarly do no update. That also makes sense, right? Because the model is already really good at whatever that prompt is. So why would we change it at all? The only updates that we're performing are when there is some non-zero variance in the group, where some of the examples are successful, positive reward, others are not. That's when we're actually doing this update. Does that make sense? Yeah.
But in this case, if you wanted to use the clipping that we did with 1 minus epsilon and 1 plus epsilon,
Yeah.
this is so rare compared to all of our other rewards in our group. Wouldn't that be not allowed for this model to be updated? I think like it will surpass the limit that we assigned.
So the question is, in this case, this advantage is pretty high. Wouldn't that surpass the limit that we have? Remember that the limit, the clipping threshold, is a function of the policy ratio, right? And we don't actually know what that is ahead of time, other than before any updates, we have a policy ratio of 1. So we'll always make one update. Then we'll remeasure this. And it is possible that after that update, we run into almost all the tokens are outside the region and we don't do any more updates. But I think that it's hard to know in advance, right? It really depends on what the probabilities are before and after the first update. So you can't just say for sure that all of these tokens will exit the region. All right. On YouTube. If all zeros lead to no update, how is the model nudged towards giving us a preferred output in that scenario? That's a good question. It's actually not at all nudged towards. There's nothing to nudge it towards, right? And so I think one kind of intuition is that maybe you do have some prompts for which there's never any signal one way or the other. But if you have a bunch of other prompts where you do have some a signal to learn from, perhaps by stacking up enough of those updates, the model will get better at these harder examples. So that is kind of related to the concept of curriculum learning, where you might start out by giving the model easier prompts, and then as it gets better and better at those, you then start showing it harder and harder examples that it would never have gotten correct initially. So that is something that is commonly done with these verifiable rewards. But initially, if you just started off on very hard prompts where it never gets the correct answer, you're not going to be able to change its behavior. Someone else had a question? You have a question?
Yeah, I do. For do I remember what I was gonna ask? Oh yeah. Since the what's it called? Since as we discussed yesterday after class, the inputs are like the results are not like unique. Like does that mean that like if if we have like a rare success, then it might like give a bunch of like one answers for the other answers?
Yeah, so I guess your question is there's no guarantee that all 8 of these responses will be unique,
Yeah.
right? And in the case of like a math problem,
Yeah.
if you have a one correct answer, then you will only get a positive reward when the response is equal to that answer, right?
Right.
So like it doesn't really matter if the multiple items in the group are the same
Yeah,
or not.
it-
You're still going to learn to upweight all of those.
Yeah, because then if we have like one correct answer, we want all it to just sample that.
Exactly. The ideal group would be like all of the rollouts are the exact same correct answer.
Okay.
Yeah. Yeah.
Isn't there a problem like if the model produces these different answers for one prompt? Because it makes sense that they'll all be similar if you're asking the same question multiple times. But like, how could this happen that it produces very different answers? That some of them is way more accurate than the other.
The whole decoding process is probabilistic in nature, right? We're sampling from the distribution. So, and in some cases, maybe not for like simple math problems, but for like coding, you have to produce a lot of tokens in order to complete the response, right? And so at any single time step, you might make an error, right? You might sample a token that's not correct. So all of this is trying to sharpen the probability distribution so that it gives you that single correct answer with a higher likelihood. As we'll talk about later next week, this whole process of doing reinforcement learning tends to dramatically decrease the diversity of the responses, which now that we've learned all of this makes sense, right? Once you find a response that has a high reward, you're going to just try and make it much more likely, right? So even if there are other responses that also get high rewards, but you don't observe them initially, you may not ever generate them again. Yeah. So there is a trade-off between this kind of correctness and the model diversity that is something we'll talk a lot more about. Okay, so let's do another situation here, and then we can start looking at some papers and also some demos. Okay, so I won't write this one out, but actually, the behavior of this is similar for if you have like 7 of the 8 responses are correct and 1 of them is incorrect. We'll get basically the same exact scenario, except you're putting a lot of negative advantage on the rare failure here. So the model wants everything to be correct, and if one of those samples is incorrect, it's going to dramatically decrease the probability of that. So what I want to write out is what happens when we have a higher variance group. So far we've been talking about binary rewards, which is fine in the context of some simple problems, but oftentimes you might not want a binary reward. You might have many different categories, like a rubric or something that you're able to grade your responses on. So one thing that's quite common is to do, like if you have multiple different rewards, right? You can combine them together in many different ways. So let's say you have a formatting reward, is the response in the right format or not, and a correctness reward. you could simply sum them. You could also combine them in other ways, like I will only give you a positive reward if your format is correct. So things like that. But you know, there's no requirement that your rewards are binary in nature when you're using verifiable rewards. So now let's say we have another group whose rewards are very similar to the first group, except the only winning response has a reward of 6, and all of the other rewards are 0. So here, it could be that you're grading on a rubric and there is some discrepancy between 0 and 1, 1 and 2, blah, 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 all the way up to 6. So like a 6 is much worse than a 0. So we have like one really good response and several bad responses. So here, our mean of the group is 0.75, so it's a little higher than before. And our standard deviation is also increased to 1.98. So we can rewrite this table. Ugh. All right, let's see if I can squeeze it onto here. Okay, so here our positive reward in the raw case is going to be +6 now, not +1. And when we do mean centering, it's going to remain the same. Oh, sorry, it's going to be 5.25, and this is going to be minus 0.75. So you can see that compared to the mean centering in this group, here we're making a much greater update to this winning sample. So this could be good in some cases, but if we actually normalize this using the standard deviation, it turns out that our advantage is exactly the same as the setting above. And so what this is saying is that even though this response got a 6 and all the other ones got a 0, there was still only one winning response. And you want to treat this group the same as you would the first group. So if you think about it, this like z-score normalization with the mean and standard deviation helps you kind of treat all groups as giving an equal contribution to the updates. Rather than if you just did mean centering, this second group would kind of dominate the update compared to the first group. And so there is a trade-off here that you should be aware of. If it really matters to you that this sample that got a +6 should be dominating the update, like I really want to make this high scoring, then maybe you don't want to do this standard deviation normalization. But generally, if you have groups with many different variances, and it's very common in your data set, you probably want to stick with the z-score normalization just so that no single prompt is dominating the update due to the advantage being much higher. Does that make sense? Okay, so I think that's all I really wanted to say about the GRPO advantage. And if there are no other questions, I will now switch over to some papers and also blog posts on this idea of test time scaling, just to show the impact of some of these algorithms that we've been discussing. All right. So I wanted to start by showing like probably the very first result on this whole idea of doing reasoning before producing your final answer. And that was with OpenAI's O1. So this was September 2024. The thing I wanted to highlight is this plot. So you can see that on the left, and this data set is a competitive math problem data set. So on the left is our most familiar plot where scaling up the training time compute, aka making your model bigger or your data size bigger during pre-training, what does that do to your accuracy on this math problem task? So you can see that as you increase the compute, the performance goes from like 30-something to 60-something. Now, the second plot is what was actually very striking at the time, which is this is a model where the training compute is fixed. So you train some model with a fixed data size and parameter count. And now you just scale up the test time budget. So how many tokens is it able to produce between those think and end think tags? And see what that does to the performance. And you can see that with minimal test time compute, the model is doing really bad. But as you increase the number of tokens that the model is producing at test time, performance goes way up. So basically, this is showing that even if you are limited in your training compute, you can dramatically increase your model's performance by just having it do more thinking at test time. Is everyone understanding what we mean by thinking here? Like just tokens that are not part of the final answer, but are still produced by the model. Okay, just as an example here, I did this before. Let me just copy this and refresh. Okay, so I have a model here, Qwen3-8B. This is a very popular open weight model, one of the best ones that is out there at this size. Also, unrelatedly, it's a good size for projects as well, your final projects. So it's a very capable model that you might want to check out. But this is an example from the GSM 8K dataset. So this is released by OpenAI. GSM stands for Grade School Math. So these are very simple math problems. You can see here, Natalia sold clips to 48 of her friends in April and then sold half as many clips in May. How many clips did she sell in April and May? So like very basic algebra. And there's actually an answer which includes some sort of chain of thought, like this is how many clips she sold in May, this is how many she sold in April and May. Here's the final answer after these 4 pound signs here. So we can look at this one here, which is a little more complicated. Mark has a garden with flowers, plants. He has 3 different colored plants in his garden, 10 are yellow, blah, 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 blah. So you can see that the answer has some step-by-step reasoning, and the final answer is 35. So if we just put this thing into, I'm going to put it into the large pre-trained model here. So this is our best pre-trained model that we have on OpenRouter. It doesn't have any instruction tuning or RL applied to it. So if I paste in this output here, sorry, this question, it does not answer this at all. So that's not great. Let's see what happens if we try the instruct version of this. So this model has been trained with supervised fine-tuning as well as some RL, but the RL is done using a reward model, not with verifiable rewards. And this model doesn't have any sort of special thinking token, so it just produces the answer directly. So let's see what happens here. Okay, so the base model, again, not really doing anything relevant. The instruction tune model is actually gets it correct, but you can see that this model generates its chain of thought and then produces the final answer all within the same response. So there's no real distinction between the thinking process and the final answer in terms of the special tokens. So this model was trained before O1 and DeepSeek were introduced, and it did not have this concept of increasing the test time token budget of the model to improve the performance. Now we can try Quen 3. Maybe you can use a bigger one than. Yeah, why don't we try this 200? Oh, wow, they have a 480B. All right, let's try this 235 billion parameter model here. Okay, so you can see here that unlike the other two models, there's this reasoning thing that's happening right now. So it actually hasn't even finished, or it hasn't even started producing the final answer. So now it's producing the final answer with all this nice formatting, and it has the final answer in a box here. But if we compare this to the llama response, here we see the separate box for the reasoning token. So these are the tokens that the model generated between those think and nthink tags. It says yellow plus purple equals 10 plus 18 equals 28, correct. So it seems to be trying to like verify its own intermediate responses. That seems right. And then you'll see this, wait, let me make sure I didn't misinterpret this thing. Wait, the problem says blah, 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 blah. Yes, that's how I took it. Another possible misinterpretation. So it's like kind of just like rethinking its initial assumptions and double checking, triple checking, and then it kind of makes all of its thoughts into a cohesive answer with good formatting. Although this is a little excessive, I don't know why it's doing this. Substituting the value of yellow. Okay, so now one thing that you might be wondering is, so this kind of behavior was elicited through this RLVR training, where they gave it a bunch of math problems, they had it do the thinking, and then they trained it using GRPO with the correctness reward. And so this kind of training really helped to get this behavior. But, you know, is that really, like, does this behavior, like, wait, let me make sure I didn't misinterpret this, this kind of backtracking behavior, is that actually something that just arises organically from the RL process? Or is it something that was kind of injected by the developers of these models? So the answer is a little bit complicated. We'll discuss this more later, but so far we've talked about pre-training and post-training. There's a third concept, which is very annoyingly called mid-training, where people inject some of this instruction following data during the pre-training process. And supposedly it helps quite a bit at unlocking certain abilities earlier on during training. Oftentimes when people are training these kinds of reasoning models, they have examples of like how they want these reasoning chains to look. Like they might have collected some data from human labelers that has examples of like backtracking or planning or more forward-looking, things like that. All of these examples demonstrating desired reasoning abilities are kind of injected during this mid-training phase. So basically in mid-training, like some of the batches the model sees during pre-training are replaced with instruction following type data. It's very annoying. No one can really study this concept because pre-training is so expensive itself, and then deciding like where should I start adding these instruction data, how many batches should I add them for. It's all more of like a alchemy rather than a science at this point. So different labs do different things. That said, there's kind of hypothesis that a lot of this behavior that we see here is not some sort of like new behavior emerging from the model, but rather the developers kind of encouraging this to occur by giving the model data that has these properties. Okay, what else do I want to show you? Right, so there's this paper which I updated on the website, is a very interesting paper that they basically just read a bunch of these reasoning chains for many different types of tasks and kind of categorize what is actually going on in them. So I wanted to show you some of these. It sounds like a very painful paper to write, honestly, with a lot of like AI text that we're reading. But I wanted to show you this figure first. So this is kind of like a better demonstration of what we just saw with the Llama and Quen models. So James writes a 3-page letter to 2 different friends twice a week. How many pages does he write a year? This is what GPT-4o did, which it has this like chain of thought prompting. Here are the steps I want to do, and then computes the final answer. This is what DeepSeek does, which it includes a lot of these like more human-like, let me think about this. Wait, let me check that. Alternatively, let me confirm. I need to double like all of these things are not really what we would expect a model to say. They're more informal. Nevertheless, that is what we observe in these models. So, and here you also see the specific think and end think tokens and the final answer. So these authors basically read a bunch of these, the text within the think tokens, and started to categorize them. So I wanted to go through some of the categories here. They have some nice figures that, yeah, so this was pretty interesting. They find that the reasoning chains generally start with like a restatement of the problem. So this might seem like a waste of tokens, but you should always remember that just because the model produced these tokens, like it's redefining the problem, it doesn't necessarily mean that the model is relying on what it produced to get to the final answer. Those are just tokens that it is generating, but it doesn't mean that it's actually even following the steps that it laid out in the thinking process. We have no way of knowing like what is the model actually doing to solve the problem versus what is it producing in the thinking process. So, and it's kind of similar to humans that way, right? Like for a math problem, I could tell you what steps that I took to get to the final answer. But for other tasks, it's less clear. So if you ask me, like, how did you decide what topics to cover in this lecture? I could probably tell you something, but it might not be the truth, right? I might not myself know why I'm covering this particular paper. Similar to that, it's hard to like know confidently or trust that the thinking tokens generated by these models are faithful to the whatever internal process is used to get to the final answer. Anyway, they find in this paper that the thinking tokens, they generally perform this kind of decomposition of a problem into simpler steps, which they call the Bloom phase. And then they have this reconstruction thing where they observe that the model comes back to things that it's already generated and tries to think about whether they're correct or not. Are there other possible interpretations, things like that. And so given these like high-level steps, there was another paper from Stanford where they were like, okay, well, do I really need to do any training in order to get this behavior? Or at test time, can I simply force the model to produce tokens like wait, but while reasoning, right? So if I'm somewhere in the decoding process and I'm sampling a new token, instead of sampling from the distribution or sampling the most probable token like we would do in greedy decoding, what if I just force the model to produce the word wait, comma, but during the generation process? So this paper is called S1, Simple Test Time Scaling. And what they do is they set a budget for the number of thinking tokens that the model will produce. And they want the model to produce at least this many thinking tokens. The way they enforce this is that during the thinking process, if the model is trying to produce the end of or like the end think tag before the thinking budget has been reached, they simply just append wait, comma, and then let the model generate more tokens. And they repeat this process until they hit the thinking budget. So you can see it here. How many letter R are in the word raspberry? This is what the model thought, and it got it got to a final answer. The number of R's in raspberry is 2, and it hadn't hit the thinking budget yet. So they're like, wait. And then they generate more tokens, and in this like heavily cherry-picked example, the model is able to get the correct answer after doing more reasoning. It even then says my initial answer was incorrect. The final answer is 3. So, there are some debates about, like, is a simple strategy like this, because they also see big gains from doing this, like increasing the thinking budget by simply force generating weight also gives you big gains on these tasks. I think they have a figure. Yeah, so you can look at it here. Average thinking time in tokens. They use this like budget forcing method and show that if you just force it to think more, its performance goes up. So overall, training still seems to help for a generalization to many different tasks, but it's clear that the model just producing more tokens also helps its performance regardless of if it's been RL'd or SFT'd or things like that. Okay, so at this point, where we are in the class is, I'll get to you in a second. We have completed discussing all of the RL algorithms that we'll talk about this semester. There are many other algorithms that you may be interested in. We did not, for example, talk about DPO or related algorithms, which are also quite popular. So I'd encourage you to check those out if you're interested. But now we'll kind of switch over to evaluation of language models, which we have not covered since talking about perplexity. Perplexity is not a good metric when we're looking at these way more complicated tasks. We will also start talking about agents, which we haven't touched so far. And we'll kind of get out of the low-level details and start talking more about applications, data, and evals. So that is where we're going. Before we end, you had a question?
So basically, because of the weight token, the model assigns a probability to look after its answer?
So let's say that the model has put a high probability on the end think token. So it wants to stop thinking and produce the final answer. At this point, if we have not hit the number of thinking tokens that we want the model to produce, instead of having it sample the end think tag, we will force it, like do a constrained generation to basically produce the word wait, which always will have non-zero probability. Like every word in the vocab will have some non-zero probability. But by sampling normally from the model, we might like very rarely have produced the token weight. But in this paper, the authors are like, well, if you produce the word weight, the model is likely more incentivized to reconsider what it just produced. And so that's the idea here. It's a very simple hack, but it also works, right? So, you know, it's worth mentioning. All right, I will take your question after class and see you all next week. So what's your question?
Yeah, so